Hey everybody, in this video we're going to look at integrating with respect to x and with respect to y, which are kind of reviews over what we've done in the past. We will be looking at functions of several variables and doing that, so this is going to be a nice follow-up to partial derivatives going the other way. Then we will finally look at an iterated integral, and those are when you have double or triple integrals and you have to integrate with respect to one variable followed by integration with respect to the other variable. And we'll get into those. Let's do a little warm-up round where we integrate with respect to x. Let's integrate from 1 to 2y. Our function has two variables, 2xy. So this would be your f of xy function. You look at the differential back here, and that tells you what variable to integrate with respect to. So integrating with respect to x, you expect to see a dx back here. The x term, when you find the antiderivative, remember to add 1 to the power, divide by the result. So this x term will be x squared over 2. So we have 2 x squared over 2, and then y is considered a constant. Whatever variable you integrate with respect to, if you're looking at a definite integral, that variable is the one that catches your upper and lower limits. Now I'm going to go ahead and cancel these 2's, so we have x squared y. We're going to evaluate at 2y and at 1. Again, substitution into the x variable. So it will be 2y quantity squared times y minus 1 squared times y. That's 4y squared times y is 4y cubed. And 1 squared times y, that's y. So 4y cubed minus y. Let's integrate with respect to y. Now, if you're specifically told a variable, that's the differential you should see. We're going to integrate from 1 to x. Our function of two variables is 2xy plus 3y squared dy. So our first term, the antiderivative with respect to y, will be y squared over 2. So we have 2x, y squared over 2. The second term, remember to add 1 to the power, divide by the result. So that's 3y cubed over 3. We can cancel these 3's and those 2's. So we're going to evaluate xy squared plus y cubed at x and then with 1. Remember, check your differential. That tells you what variable catches these two values here. So that's x times x squared plus x cubed minus x times 1 squared plus 1 cubed. So this is x cubed plus x cubed, that's 2x cubed, minus x minus 1. Okay, now suppose we take that function and we set up a double integral where the outer differential goes with the outer integral. Remember, the integral symbol is just an elongated s for the limit of sums. From the example right above, we integrated this function from 1 to x with respect to y. It's identical. So I kind of cheated and worked this out ahead of time just above. But anyway, this inside box, and when you work a double integral, you work them inside out. We have 2x cubed minus x minus 1. So I went ahead and cheated and put that in here. It's not really cheating if you've done the work. Now we can address this outer integral and outer differential. Antiderivatives with respect to x, we're going to have 2x to the 4th over 4 minus x squared over 2 and minus x. Substituting in a 2 and a 1, I'm going to go ahead and simplify that to 1/2. So we have x to the 4th over 2 minus x squared over 2 minus x. Let's put a 2 in for all the x's, and then turn around and subtract, and then put a 1 in for all the x's. Feel free to use your calculator if you need. This first box gives us 4. That's 16 over 2, which is 8. Minus 2 is 6. Minus 2 is 4. This minus sign and that one's the same one. 1/2 minus a half is 0. Minus 1 is -1. Grand total 5. In that previous example, we could define our region. X was from 1 to 2. Y was from 1 to x. And we can set up our double integral this way. R is the region of integration. The area of R was 5 from the previous problem. Excuse me. Now there's a couple of ways to set these up. The area of a plane region can be vertically simple, closed in from the left and right by 2 constants, closed in from the top and bottom by 2 functions. If you look at it through the eyes of vertically simple, you're going to think of it as that representative strip of delta x. That's the little bitty tiny change in x. That will be your outer differential. The outer integral will match the x value. So a to b in the x direction, the differential of x. Inside, the differential with respect to y will be from the lower function to the upper function. Now, if you change and you look at the area of a plane region that's horizontally simple, and sometimes you have regions that are both, then it's dealer's choice on what order you go in. But if you have your representative strip going horizontally, call it delta y, then delta y will be your outer differential. The first integral will be the parameters, I guess you could say, the limits from bottom to top in the y direction. And then the inside will be your differential of x, and it'll be the right function minus, the cutoffs of the right and the left respectively. The lower will be the left cutoff, the upper will be the right cutoff. Use an iterated integral to find the area of the region bounded by the graphs of sine x and cosine x between pi over 4 and 5 pi over 4. Okay, I sketched in the graph of sine x, the graph of cosine x, and I just chose to do vertical. If that's the way you do it, then these two graphs intersect at pi over 4 and 5 pi over 4. And if you think about it on the unit circle, at pi over 4, which is where 45 degrees is located, sine and cosine are both square root of 2 over 2, so they're equal. At 5 pi over 4 in quadrant 3, where 225 degrees is located, both sine and cosine are negative square root of 2 over 2, making them equal. So they intersect at pi over 4 and 5 pi over 4. So that's why I chose these as the lower and upper x limits. I was sure to put dx differential on the outside. Then on the inside, sine is on top of cosine. So we're going to need to make sure sine is the upper limit, cosine is the lower limit in the y direction. Remember to work these inside out and you'll get the area of the region shaded here. There's an unwritten one, so when you take the antiderivative with respect to y, you get y evaluated at sine and cosine will be sine x minus cosine x. Then we move to the outer parts. The integral from pi over 4 to 5 pi over 4 of sine x minus cosine x, differential x. Take the antiderivatives, you get negative cosine x minus sine x, evaluated at 5 pi over 4, subtract, and then evaluate at pi over 4. And that's written here. Take your values from the unit circle and really watch your negative signs. There's a whole bunch of them in this one. Positive square root of 2 over 2 plus another square root of 2 over 2 makes square root of 2. And then back here, positive, positive, another square root of 2 from the back set of brackets. And that gives us a grand total of 2 square root of 2's. Now let's look at comparing orders of integration. With vertically simple, and I'm just going to take a function that we're used to seeing, square root of x. We're always used to seeing it y in terms of x. Y equals square root of x. Okay, so if we draw a vertical horizontal representative strip, then we're going to put dx on the outside. The x direction goes from 0 to 4. That's also on the outside. Now, in the y direction, we're going to go from 0 up to here. Well, that upper cutoff is your function, square root of x. And that's how you would set that area up for vertically simple. Now, if we do horizontally simple, same function, but now x will be in terms of y. Exact same curve. If we take the horizontal strip, delta y, then that means dy is outer. The y direction goes from 0 to 2. 0 to 2. In the x direction, we go from the vertical line x equals 4, trapped on the left by our curve x equals y squared. So remember, it's right on top, left on bottom, 4, and y squared. Simplifying, x equals y squared. From the previous page, and if you need to rewind and go back and look at the diagrams again, that's totally fine. We're going to integrate with respect to any direction. Either direction is a better way to say that. So let's do it where it's the horizontally simple. That was the top diagram on the last page. So we're going to antiderivative will be x evaluated at 4 and then y squared. Remember, work them inside out, so that's 4 minus y squared. Now we take the antiderivative with respect to y. 4y minus y cubed over 3, evaluated at 2 and then 0. So 4 times 2 minus 2 cubed over 8 minus 4 times 0 minus 0 cubed over 3. That back half goes to 0. So this makes 16 thirds. The second diagram from the previous page was vertically simple. And so we put the dx on the outside and the x limits on the outside. Starting on the inside, our antiderivative will be y evaluated at square root of x and 0. So that's just square root of x. Remember, this can be written as x to the half. So the antiderivative will be x to the 3 halves divided by 3 halves, which is the same as multiplying by 2 thirds. And then we'll sub in our 4 and our 0. That's 2 thirds times square root of 4 cubed minus 2 thirds times square root of 0 cubed. Well, that goes to 0, so we have 2 cubed is 8, 16 thirds. Matching answers. And that's the way it should be. That's your area. Sometimes your areas and your regions can be broken up. I just wanted to show you an example of that, and this is what this example pertains to. Find the area of the region that lies below the parabola 4x minus x squared, and that's this arch, above the x-axis, and above the line y equals negative 3x plus 6. Now, one property of these double integrals is you can add those up. Like, I made this design to represent R1. R1 is trapped between 1 and 2 in the x direction. It's trapped on top by 4x minus x squared, and it's trapped on bottom by this line, negative 3x plus 6. That's taking a vertical delta x strip. Region 2 travels from 2 to 4 in the x direction. It's trapped on top by 4x minus x squared, and 0 in the y direction. Working inside out, notice that the full area is R1 plus R2. So down here, the total area will be the area of region 1 plus the area of region 2. Region 1, starting on the inside, the antiderivative of this unwritten 1 will be y. 4x minus x squared minus negative 3x plus 6. When you combine like terms, you get a negative x squared. 4x minus negative 3x is 7x. Minus 6 is negative 6. Then on the R2 integral, working the inside, the antiderivative is also y. Evaluate at 4x minus x squared minus evaluated at 0, so that's 4x minus x squared. Back to the first integral. Antiderivative with respect to x is negative x cubed over 3 plus 7x squared over 2 minus 6x, and that will be evaluated at 2 and 1. The second integral, antiderivative with respect to x, will be 4x squared over 2, which is 2x squared, minus x cubed over 3, evaluated at 4 and 2. So evaluated at 2 minus evaluated at 1, and just be careful calculating, you get 13 over 6. Evaluated when x is 4 minus evaluated when x is 2, you get 16 thirds for a grand total and reduced 15 halves. This would be 32 over 6. 32 would make 45 over 6, but it reduces to 15 halves. This is the start of Unit 4. It is Chapter 14 in your book, your e-text. And anyway, I hope this video helps you kind of make sense of what you read. If you have any difficulties or troubles, reach out by email, phone, or swing by the office, and I'll do my best to help you out.